Thank you very much for coming for today's talk, and also appreciate very much for the invitation from Research Triangle AI Society. So if you have difficulty hear me or see me, please see something in the chat. But during the presentation, during this time, the talk, I don't have time, energy to see the content or any question in the chat. So if you do have some technical question for me, please leave in the end, so we can have a question and answer session in the end of the talk. So now, because we have a lot of to cover, I will focus on the content of the presentation during the first 45 or 50 minutes. Okay, today, again, the topic is how to create, distill, and prune your own small language models. My name is Paul Liu from NC State. And the outline, the content of today is we will talk about what is the large language model, and then we will see how to create a small language model from scratch. For example, a GTP2 level, that kind of a small model, and how to distill and large language model to a smaller size one. Particularly, I will give a sample case, how to from the Q1, the Qianwen, to the DeepSeek. This is a popular one. And then what is the reinforcement learning, the RL, the very popular one. What is the RLHF? This is the reinforced learning with human feedback. And then finally we will talk about how to prune a large language model to a smaller size one. So first, as always, I want to say something at the beginning of this talk. This talk is not designed for computer science major or AI or large language model field scientists or engineers. So if you are already an expert, you are very well in this field, and you do not really need to waste the time here. And so instead, this talk is for beginners or dummies like me, so without too much background or experience. This is an introduction, or we will show many case study demo for you to get many aha moment. Many sample we will run. You can also run like what I will show to you, something you will say, now I know it. I can do it as well. This is for you. So particularly for those who have no idea how to handle large language model. So like the previous talk, we will remove the fear, give you confidence to gradually enter in this field. This is the purpose. So all code will be shared for educational purpose and further improvement. They are not for real world usage. So I think, as always, I like to start our talk from this overview about AI, machine learning, deep learning, and generative AI. So in particularly in machine learning field, let me change. In a machine learning, we all know traditionally there's a supervised machine learning like a regressional, like a Distilling tree, random forest, or support vector machine, or sometimes unsupervised machine learning, all kind of cluster, K-mean cluster, or some kind of PCA. And in deep learning part, sometimes we will see very traditionally commonly term you heard, like convolutional neural network, CNN, or some kind of like a DNN, deep neural network, or recurrent neural network, or transformers. So this is a kind of like a deep learning portion. And then we have regenerative AI and large language model. The large language model is a subset of those deep learning, like from transformer and generative AI. So in terms of generative AI, that means we can have all text, image, voice, video, or even structured data as input. Then we pre-training all the information, then put the neural network model, then fine-tune them. Finally, we're able to question answer. We can produce the content. We even can produce the voice, video, generated like animation. So we even can predict the consequence or event. So that's the future of generative AI we are talking about. And so as always, I strongly recommended everybody who are interested in large language model watch this 1 hour talk given by Andrea Capacci. So who is he? He is just a unbelievable guy. And if you look at his resume, he's the former director of AI in Tesla, also one of the co-founder of OpenAI, and a former research scientist at the DeepMind or Google. And he got a PhD from Stanford, studied with Fei-Fei Li, with Li Fei-Fei, his PhD advisor. And he's a strong advocate for open source AI. And so he's just a guy sitting on top of this field. And who we are. And maybe some of you already in the middle, but for me, I'm here. I'm that little baby still sitting on the floor. Maybe I'm just in the first floor in the lobby. I haven't really entered into the elevator. So there's still a long way to go, but I have a lot can learn from him. So the reason I mentioned him is this. Because our first case, our first thing I want to show you to how to create a small GTP2 from scratch is based on his talk. So the first video, let's reproduce ChatGPT2. This one is a 4-hour demo. So I watched that in about a year ago. And also this one just like 2 hours, a little bit shorter. So based on these two demonstration, so we are able to say what is the GTP2, what is the architecture of the GTP2. So look at this one, because this is the only GTP model that OpenAI open sourced, not open source, it's kind of open sourced and released the architecture. So if you look at this one, we see the import, then through many transform layer, then we get the output. So if you look at each individual transformer layer, you can see there's some normalization layer, multi-head mask attention, drop out, normalization layer again drop out. And if you look at the multi-head layer again, there's many details algorithm, including like a software max to handle the output and how to list protocolize. So this is the internal structure. Based on this architecture, now we are able to see how we can build one from scratch, from zero, doesn't base any other model. So this is the flow chart. For example, we have an import sentence, the cat sat on the mat. So first of all, because the model cannot really handle the word or character, but we have to index, we have to token or tokenizing. We divide the whole sentence to individual unit. This is the per token. That token, we have to encode them. And so in this, we have a different layer to handle all the training material. So basically, a large language model have this 7 basic layer. We have embedding layer. All the data you have to convert, and after tokenization, after encoding, you have to put an embedding layer. Then you put in position, attention layer, and feed forward layer, and normalization, residual, output. This is the basic, very, very basic layer. So with this, and if you look at the GPT-1 to GPT-4, as you can see, the parameter GPT-1 have 100 million parameters. GPT-2 will be 1.5 billion. GPT-3 will be 100 billion, and GPT-4 is almost 2 trillion parameters. In terms of the layer, the GTP1, this is a couple years, 6 or 7 years ago, is only about 12 layer. Then GTP2 jumped to 48 layer. GTP3 is 96, and 4 is 120. And if you look at the open source Llama 3.1, the 8 billion one have 32 layer and 4,000 dimensions and 32 head. And also the K value is about 8. The reason we mention this, but very soon our first case, we will use all the term to twist around in our code to try to build that kind of very simple, small, large language model. So we had to deal how many head we have, how many layer, how many, even our vocabulary size. Okay, so this is a very basic, now you have a little bit pre-taste what's the large language model, how they handle it together, what's the flowing chart. And maybe you also heard about scaling law. Scaling law, when we talk about the size, parameters, layer, head, all that kind of thing, there is an important term called scaling law. Scaling law is kind of to deal the performance or the relationship in the machine learning model. What's between the model size, how many parameters we can use, how big of the data we can train, and then what's the computational resources. So this is the between. We need a bad performance, but we don't want to have a huge model size. And also we hope to have a moderate or even smaller hardware resources requirement. So that's kind of the balance. So this is at least for So now let's look at a little bit detail each layer. Particularly, let's look at it within the attention layer. In the attention layer, there is a three key character. Three key one is a query, is Q, key, and value. For example, we have the cat set on the mat. So now we put a token. Token is the smallest unit of your input or training data set. Then for this one, we have to see in this one, what is the tension, what's the scoring, within the process. Actually, this process is kind of matrix, multiple matrix. What's the relationship? When we have the cat will be set. We cannot see cat fly, right? So barely see cat swimming, right? Something like this. We build all those kind of relationship token between the token. Because, of course, that token we will have to digitalize. We have to encode them. We not really use the character, the word. We have to convert to a digit. So later on, I will show you exactly what we talk about. Then, for example, we will build each word. What's the next sequential future prediction with all that kind of relationship with kind of the weights. Then we store all the weights. After training, after so many rounds of the training, we store those relationships into a very special matrix. That matrix is called tensor. In tensor, maybe if you're not very good at statistics or mathematics, maybe this is a very strange word for you. Maybe you heard about array or matrix or list, but tensor is a very, very important one for large language model, for artificial intelligence, particularly large language model training. So, for example, all the information, all the weight, all the relationship, can store in the tensor. Tensor is a multiple matrix. So each layer, each dimension, you can save text, you can save a digital number, you can have voice, you can have image, or you can have time series data. So it's a kind of a multiple layer of matrix built up together. This is a tensor. So because in Chinese way, you say 张量. 张量 is maybe much easier for you to understand. So there's two very short but easy understand YouTube. You can watch it. So one is called simple tutorial on tensor. The other one called machine learning layers, the tensor manipulation operators. So go ahead when you have a chance. But by the way, I will share my slide to everybody who are interested in. So if you watch the recorded one, you can send us an email. We will share to you. So So then you can get a link, or you can just search over the YouTube. So all when we talk about all attention layer, there is a key paper published by the Google Research Office. So the team. So this is the one is a master read paper. Okay, now let's look at our first example, how to build that the GTP. So the first portion of the code is based on the YouTube, as I mentioned, the 4-hour and plus the 2-hour one from Zero to Hero video series from Capacity. So this one, I want to give you a very quick view how to build this one. So let's shift to this one. Don't worry about now, and because I realize if I give you the code a link now, you will play around. We have issues. We'll slow down based on our previous presentation. I will give you the link in the end of the talk. So here we are on the Google Colab. So if you have a Google a Gmail account, you will able to access the Colab. So in the Colab, you can, if you are free account, you can access the CPU, of course, T4 GPU, V2 GPU. And now I want to use the A100 for give you a quick demo. For example, now, I don't need to do this. So for example, we can download the data first. So the data set we use is a Shakespeare text. So now we download. If we look at the detail of the data itself, as you can see, this is all the dialogue of the whole book. So now we can see, now we can read this text file. You can use the text file, you can use a CSV file, or any text material, as kind of a training to build this small large language model. So as you can see, we read in, we can print out the length of the whole character of our data set. This is the length of the text we have. And also we can see the first 1,000 sample, as you can see here. Then we found out based on the whole data set, the text body, how many unique characters inside the character. So we can find out, we can sort it out. Okay, we found 65, including all the symbol. The capital letter 26, then the small letter 26, this is 52, then plus a couple number, and only the number 3, and a couple other symbols or punctures. So now only 65. This 65 means our vocabulary size. I hope you remember when we talk about the large language model, the vocabulary is huge. And here is a very simple demo. This is just a 65. That 65 is not based on the word. We actually based on character by character. Our token is character. Is not the word, because this is the small one. We want to be a quick demo. So as you can see here, totally is 65. Then now we can build our own dictionary. So dictionary, if you build the word, your dictionary, your vocabulary size could be 60,000, right? Or up to couple thousand. So, but if we based on the character, we're only 65. So our dictionary is very small, very easy. So now we build our dictionary. Dictionary is basically we can convert each those character to a digits. So each character have 2 bytes. So now if we can see very simple function. So for example, we can convert hi there to the digit. This is the digit, hi there, something like this. So we can do a decoding, we translate back. So like this 3 character now is hi, and this is there. As you can see, now you understand the logic. Now we can build based on that data set to build our tensor. So that tensor, what that means is, first of all, we convert all the character, all the text to the digits. This is our data set. And with these digits, now we will kind of first we spread all our data to training and the evaluation. So very simple. So after do that, we defined our block size. And what that mean, block size? For example, we have all the data. We cannot read the whole data at once in one time into the memory because, the data set could be a gig or 100 gig or terabytes. So every time we only to read small portion of the data and randomly and sampling the data. So we defined, okay, this is the block size, and then we block size. So as you can see, is 8. So we have 8 digits, okay, come out from our digitalized data set. And then, we can build, as you can see, gradually. So the next, we want to say, we will build a batch size and block size. What's mean of the batch size? Here, I wrote very detailedly of the explanation. So after I share this one to you, when you play back, you can read it, understand a little bit detail. So here, I want to shift it back to our PowerPoint. I want to explain to you what's that mean of that block size or a batch size. For example, here, we want to convert our whole data set to based on our batch size and block size. So for example, here, we have a random choose. The random here is the key. So for example, from the whole big data set, we can find out the our based on the block size. The block size is 1, 2, 3, 4, 5, 6, 7, 8. And this is 4 by 8 like array, right? This is a very simple tensor. This is the array of matrix. So this is the 4. The 4 means I have this 4 batch, and each block have 8. The size is 8. Okay, I have 4 pieces. Each block, the size is 8. So this is the data I can randomly choose sample, okay, from our big data set. And then use this one, we can also to predict the future one. So let's go back here. So this give an illustration. I haven't seen anybody to show this to the audience. So this is the thing I used for the training and or in the classroom. So this is your data set. For example, we have 4 batch and each block is 8 size. Now the first round, we choose the 4 block from our data set. Each one have 8 size. From 8, 1, 1, 2, 3, 4, 8, 1, 2, 4, 4, 8. This is randomly choose. And this is the first round. Then after the first round, and we can do a second round. So again, we do a 4 block, each is 8 size, and again. So finally, when we randomly run enough, we almost will maybe repeatedly overlap all the sampling data. We will cover it. We will use it for the training. So now you understand what's the heck going on of the training, sampling data, what's the batch size mean, what's the block size mean. So after that, for example, we have the import. In the first round of import, we have the 4 by 8, as I explained earlier. Then we can have a target. What's the mean of the target? For example, we have 24, 30, 42 to all this way. Because next one, we will start in 43, 43, 84, this one, then ended here. Then we're able to know next one is 39. Then similarly, this block, we have, 53, 56, 1, then until 58. Then next one is 1. So as you can see, we will do a array by array, metric by matrix, import, output. Then we build that relationship. All those relationships will also store in a torch array, a torch tensor. So now, okay, after we go back here, so now we can go jump all the way, this is the prepared data set. And then we can build the simple model. That simple model called is kind of diagram model. Is very, very simple one. So, this one, as you can see, we only have that kind of forward have here, have a forward function. The generate function is kind of like a predict the next one. So this is a very simple model. So as you can see, we can build the torch size, and then the relationship actually is the math, is how to multiple them, how to get the data. Then we don't want to go to detail. You can read it detailedly, all the note are put here. So this is, then all the diagram including here. So I put it for student during the last semester. And now we can go directly to the fully finished code. That's very simple one. So for example, we defined the pet size 32. So this now is not full. We can pick up 32 blocks from the data set. Each block is either 64 or 32. This is important because the batch size and the block size will determine your memory, how much memory you will use. So you can read a little bit carefully all the comments, all the notes are put there. So the original one, capacity original code, they don't have all the explanation built in here. So for example, here we have a learning rate as in the beginning when we show the GTP. Then we have how many bedding layer, 64 bedding layer. We have a head number 4 and the layer is 4. Okay. This is the code and also vocabulary. This is the standalone, the full working code. And also, as you can see, you defined the how to the class of the head, and also the multi-head class, and the block size, and this is updated code, and also the simple model. So now we can run this one. So when we run this one, as you can see here, so this is use the one single GPU is running this. This is take about a couple minutes. So as you can see, step one, totally we have 5,000 steps, but this is only one epoch. So the real case, we will run, I have run the 30,000 steps. So I will show you later. So now we can stop. Oh, how about I just let it run a little bit. So as you can see here, this one around the 30,000 steps. As you can see, all the training loss and the validation loss gradually to a certain level. You do not really need to extend any further running. And based on the size, then you can save the model to the local, and also can upload your model to Hugging Face. So you just need to change your own username, and then you can evaluate. So for example, in the end, and the result is something like this. And this is the testing of the model result. You can run the code after you get the link. And so, for example, this is you give a little bit import. For example, here you can see, oh my lord, and then where the import here. This is loading the model, and the import is, I cannot see now. The generate one, the model loading here, the import, the training data, and then the text generation. Oh, this is based on the import from the training data. So now you can see this is the generation. Very small model can have the consequential prediction of the character come out. So at its side, make me on the survey, something like this. Some is not really, but this one not bad. He's, at least they have some character. The word by word is a meaningful word. And if you only train 5,000 steps, and it doesn't really mean too much if we look at the original code. So I also updated this code. As you can see, you can run much more meaningful one, and you can have more step come out. You can have more time control. As you can see, the generate out if hence and where you so mom, lady, gray, something like this, all the kind of result. And so you can play around. This is a little bit different from the original code they provide. But what I want to say, this is a one single GPU we play around. And to at the same time, if you want to run a multiple GPU, so we have to use the distributed data parallel. So, for example, many of you have a PC, have two GPU now already. So you can take advantage of them to run this. Here, I just want to give you another demo how to use the HPC. And this is at NC State HPC. We are able to access multiple GPUs here. As you can see here, so I'm working under my current working directory. For example, if I go to GTP2, so this is the GTP2 run. I run more dataset and much more epic and steps. So for example here, and this is I show you the one with distributed data process. This one, for example here, as you can see, is almost similar, but here I included this portion, the parallel, the distributed data parallel DDP. With this one, we can check how many GPU we have in the system or available to us. And then, we can calculate the time, estimate, set up the DDP. As you can see here, clean up the DDP after the running. And then all those are same as the collab. And then if we move to, so of course, this the diagram is a little bit complex than the original one. So if anybody interested in this DDP, you can contact me. I can share this one with you. So for example, we run the DDP setup here, and then we can see how many rank, how many, the host, how many the hardware we available. Then if there's a multiple one, we can distribute our work, our data set and different step. We run parallelly. So this is the code. I just want to give you a quick demo how this looks like. Okay, let me see. And so where's the okay. So for example, I want to maybe try two or three GPU here. And what I need to do, I request a temporary, for example, here, maybe I request a temporary, let me see if I have able to have a full GPU or not. So this just, let's see if maybe together with choice was 800, not only H100. So this is a temporary 10 minutes request. Say if the system have a full GPU at one host or not, maybe not. If not, I just decrease. So I try a moment ago, and so this one not available, but I can try to run at 3. Okay, now it's available at the machine 13 GPU machine 13. I have 3 GPU available. So at this moment, I can just have turn on my working environment. So I just active my Python for this project working environment. Now I and this MiniMind working environment. So at this now I can test my the distribute processing. So let's say if I do this, I can run this one here. Oh, sorry. So now I have 3 GPU. So now I have 3 GPU. I'll try to run this program. And now I have the total run. As you can see, I have 3 GPU available for me. And so it's parallelly processing. And now you can see it started. This is just a demo, and my real work I'll have to submit. I have to wait, and so sometimes very quickly, sometimes need to wait a little bit longer. And but automatically, when the GPU, the hardware resource available, will automatically start up. So as you can see, it's gradually to pick up, and it is running the job. And on the 3 GPU, this is a 3A100 GPU. Each one have 40 gig memory. So as you can see, they were definitely is much faster than the Google Colab working environment. Okay, so can say let's wait one more round, then we can stop here. Okay, we can stop here. So now I just want to show you, and this is a model running result come out with the training. So it is a couple one the training here, and I can show you the record here. As you can see, this is the 4 GPU. This is the last time around with the H100. So as you can see, so around the 4 epoch, each one is about 8,000 steps, as you can see here. So this is to give you a pre-test. So now we shift it back, and so all the code we'll share with to you and from the Colab. And so after we run, as you can see, we can get a prediction. We can have the next token be predicted, but still not good for the chat or dialogue. So in order to do that, we need a fine-tune. So this is the regular procedure. We need a pre-training large without the label, without the structured. So the large text-to-text, pre-training, then we need a labeled and defined data coming to the fine-tune. Then even not the fine-tune, sometimes not enough. We also need this kind of reinforcement learning and with the human feedback. This is actually the real industry procedure. So here, we just want to give you another very, very real, useful, small large language model called MiniMind. So the one I showed to you, GTP2, this is only for in classroom for demo, was the concept for you. But this one is, you can really pick up this one for the real work. And so as you can see, the structure, the architecture is almost the same. We have this kind of tokenized encoder. We have embedding them, transformation layer. Then finally have softmax, then tokenized decode back, then gets the result out, the output. So again, each layer, we have that kind of, a different how to handle them. So that small large language model, 26 million parameter. The model size is only 109 actually, 110 megabytes. So it's very small, it's very portable, and actually it's pretty amazing. And as you can see, this one can have that kind of dialogue, the real dialogue. As you can see, what's your name? Of course, this one demo, he's the Chinese character, Chinese content. You can use the English, you can use any text-to-text material, like a Shakespeare one, you can throw into training. So as you can see, it's pretty good in terms of function. What they did is training the first pre-training, then also fine-tune use the chat one. Okay, the labeled one. Okay, I want to show you, I want to give you a demo. So what's going on? So now we shift back to the Colab. So here, this is the GitHub. You can see this is called a MiniMind. I will send you, you can Google, and I also send you the link. And they have the Chinese version and the English version introduction. And for example, here, this is all the introduction. This is the animation I show you. And very small, very portable, only 100 meg. And so as you can see, different version. And so this is their working environment, and they don't have any Colab version, notebook version. So I managed, put it here, So I put it in the collab again because we don't have time to run step by step. I already shared this one to you, and I will give you a copy. And so you can run this one. The key part is the data set, and the data set is about 4 gig, as you can see. And you need to process a little bit, but it is working on here, no problem. I already went through all those, and this model in the end, so it in here, Google Colab, single GPU, A100. So it, as you can see, I run 20 epic. Each one, as you can see, it take about me 3 hours. So, can you imagine? This one is a 60 hours for that single A100 GPU, and so it works. And so it's painful. What I say is very, very painful to get a result. I want to show you how it looks like. So after the run, I have an evaluation. Oh, even I spelling wrong this word. And so as you can evaluate. For example, we can test the run after model with all the input because the text in the data set itself is the Chinese, but we have a bunch of the English, pure English one. You can instead use it. And for example, he asked, I mean, for many Chinese, how many audience today here? Oh, we have 129. Oh, pretty good. And oh, many our Chinese friend, Happy New Year. So as you can see, they ask, who are you? I mean, it give a totally nonsense answer. And because this is a very quick running so far, but only the text portion. And for example, what's the best university and how many the light speed? You see, it's not make a lot of sense, but it's able to produce. I mean, sequentially produced. And for example, how about the blood? What's the component? He gives some not really right answer. And this is small model, but we have to fine tune. And we just build based on the weights, the layer. So we need to fine tune. And to do that, I cannot do this, on the single GPU. So we had to shift it back at the HPC. And for example, and I loaded here, so we can have MiniMind here. So as you can see, I already trained this model. For example, use in the out, and you can see all the model around. So all those model is only about 107 megabytes, as you can see, as I promised to you. So coming back here, so I want to show you what's the running record, the most recent one. So is like this one. As you can see, we're starting off the parameter and run 20 epoch. So each one now is only about 30 minutes. So from 3 hours, the single GPU now is 30 minutes. You can see the difference. Now I only run 4, I believe it's H100 or 800. I can't remember exactly this one. So as you can see, this is the one, and so you can run. If you have a 2 GPU, you have a couple GPU available, or if you are interested, if you have some resources, we can working together. I'll give you a code. You can run in your server. Maybe you share some. We can working together. So this one can, as we said, could be very useful because small size, as you can see, after fine tune, you can see what's the tallest mountain in the world, and he said is Himalaya, and also between China and Nepal, and how the deepest trench in the world, Mariana, Western Pacific. This is already amazing. The small model can handle this. And with this result, okay, so all the code, and they have a code. I already have a core lab version, and also I managed to run the HPC, or if you are interested in, and I share those, and also if we can working together for multi GPU. And so this is a very wonderful one. And also the good thing about this one is also trained, as you can see here, also trained the vision one. And so this is the mean. Oh, no need to show here. So there's a version for the multi version, the MiniMind V. This is the vision and multimodal one. So this one, with this one, you are able to with this one. Let's shift here. So with this one, similar as you can see, they can detect, they can analyze the image. Okay, and also this one have a MOE, the mixed of expert, and put it in here. As you can see here, this is the dense model, and this one with MOE, the mixed expert, and very open source small model, and with a couple GPU you can play around. That's amazing one. I think this is even more useful than the DeepSeek, and then we will talk about it later. So this is the great resources you can play around. And so as I see, as a demo, as a demo to you. So for example, here, this is the model I run the vision one. The vision one already, I believe, let's see. This I run a couple of times. You can see here. And you can see here. And this one maybe. You can see here. So just submit a job and then you can run it. So now this one, let's coming back here. We need to speed up a little bit. So as you can see here, this one you can play around. I put all the link there with you, and you can go there, play around. So if you can run 60 hours on the one single GPU, it's good practice. But if you have a multi GPU available, it's good. I forgot mentioned. And if you look at here, the guy put it here, that the Chinese group again, and what they have is what's their hardware? So this is his hardware, his CPU. The good thing is his memory 128 gig. My laptop is only about 32, so I cannot run this on my 30, and then his GPU is only about how many? 2 GPU, 3090 and 24 gig. It's not that advanced, So I know many members in this group, they have a 4090 and they have 309, we have this kind of setting up. So now, if we can do it, you can do it. So, but if you, like me, if you can access multiple GPU, we can run the distributed data parallel one. So, okay. Nice. Let's coming back here. And so again, as you can see, the pre-training is only the first step. Pre-training enable you to predict the next token, but cannot do the dialogue, cannot do chat. We have to run a fine-tune. And that fine-tune is the labeled data. And fine-tune sometimes is not enough. You have to optimize. So that is bring to other thing called Distill and distillation. So we all know, if you are basic middle school or high school chemical training, you understand this physical process of distillation. But in the large language model, there's also a term distillation. It's very similar, very similar. You have a big one, and you have the process, you have the receiver. So the large language model, the distillation have a 3 component. It's actually 4 component, and you have a teacher model. Then you have a knowledge transfer process. Then you have a student model, but you also need to have some data, involved. It's not only purely transfer one button. No, it's not like that. And you can read the paper by the Gu Jianping, as a Chinese guy, published in 2021, and the knowledge-based distillation. And so this is a summary book. So I come out this for my student, the process for distillation is loading the pre-trained teacher model and prepare the distillation data, and then you run the teacher model to generate a soft label. Use the teacher model of the soft label, then initialize the student model. And student model just like a container with the structure. And then you train the student model, use the distillation loss and evaluate. Then finally you get a student model. Maybe you heard this term a lot. So this is basically the basic procedure. So again, let's look at the code. So now you understand what's the heck going on. Now, what's the code tell us? Now we shift it back here, and we can look at the code. So this is how to distill a large language model. This is a procedure. And again, I run this in a one single A100. So we don't have time to run all the steps. Everything works here in this sample code. I will share this sample code to you. So I already shared. I will give you the link in the end. So and then, as you can see, we build the teacher model. The teacher model here is kind of like a Llama 2 7B chat model. Use this model, we want to distill a smaller one. The smaller one is the tiny Llama one, 1.1B, chat one, as you can see. So this is the demo. I put them together. So is not from anybody else, but I'm happy to share with you. The data set we used, we have 4 components, right? So the data set, we use the Wikipedia data set. This is about, how much? 16 gig. It's too big. So let's do a 10% of the Wikipedia data set. So 10% is a good size. And then we training the configuration, use a single 1-800. As you can see here, the output one, and how many accumulation, our training, learning rate. And I only run one epic, to save time. And a demo, you can run 5 or 10, you can try. And so you can test around. The good thing is, and then we can have that kind of a distillation process, as you can see here, is working. Then we initiate the trainer. The trainer is just a process taking the knowledge out from the teacher model, and then we feed in the student model. And then we save the student model out. As you can see, this is all the steps I take, and then we save a student model. Then we can save and test. For example, look at this. So use the distilled student model. So how to make a coffee. The response: I don't have a coffee maker, but I can give you a general guide. Choose blah blah this. This is fantastic because the teacher model is good, the master is good, the shifu is good. If I have a good shifu or teacher, master, and then, well, you most likely have a good student, right? So hopefully like some today, and some of you will be much better than me. And okay, this is one way. And the next one I want to show you is a real case. This real case is from Q1. Q1 in Chinese is Qianwen. And you heard about that 2 days, 3 days ago, 4 days ago. Qianwen come out, the Qianwen Prune 2.5 Max. They have a news, but they haven't released the with yesterday, at least. I don't know today, maybe every day changed, maybe every hour changed. They haven't released the with yet, so we cannot able we cannot deploy locally because they haven't published the weights. The weights is kind of the tensor matrix. Okay, but you can distill the Q1 to a DeepSeek model from this case study. So this code I also put them here. Load the teacher model is the Q1 2.5 mass 1.5 billion. And then after this one, you define the student model, and then you prepare the data set. Again, we use the Wikipedia one. These are many other data set are put it here. You can use the mass data set, and then tokenize the data set. Similar thing. Then you can, after you bedding that, then you knowledge distillation training. This is the code, the working code. And after you training that, as you can see, you save the model. You save that DeepSeek R1 distillation model out. And then you can evaluate the data. Then you can say what's going on. I just, that's the evaluation. We just run a very quick test. And so I put it here. I share this one to you. So many of you can play around, can improve, and then test the distilled model. Okay, here. And for example, what's the time there's a land, something, because we have very short training sample, but the island 100 miles away from the island, blah, blah, something like this. Okay. And so let me say, and hopefully I can finish soon. And, here. Okay. And now we have the last portion is the pruning, the large language model, or trimming, other way to say, to cut. And so this one is, we have to read a paper. That's a classic paper, Huang Hanjuan. I like the Chinese name. And so again, this is a collaboration between mainland and Taiwan. Fantastic collaboration. And so the idea is, this is the weight based on prong, trim. So I will give you an explanation. You will say, aha, I understand what's going on. So for example, this is unstructured or structured. So don't worry about it. You can read a little bit detail about this, but I'll give an example. For example, you have original weights. The original weights is like this, the distribution. As you remember, just like the tensor I give to you. Then you sorted weight. So all the weight you sorted, you get absolute value, the no negative value, always the positive value. Then you check what's the mean, what's the cutting off line, the threshold. Then you say, okay, I don't care about everything below this. So now I have this. Then you can get, then you turn back the original value and position. Then you get this. So this is just some knockoff, some weights. And this is a very basic principle diagram. And I'll give you an example. For example, the weight distribution like this from the original model is 0.2, negative 0.5, 1.2, 1.1, negative 0.9, and 0.2. This is the one. So now we say we want to cut 30%. Okay, want to cut 30%. How we do this? We sort the absolute value to this value. And as you can see, there's no negative one. Then we found the threshold. So you can calculate the threshold, and this is a procedure. So 30%, the total number is 6. Then you can get 1.8 is about the threshold, like a median value. And then you can find, okay, it's a 1.8. So this is a cutting off line. So this one will point when this will be gone. And then finally, you have you return back, you return the position. So this one is knock off. So you reduce one. I mean, this is just a quick explanation. Maybe I'm wrong, and because so many experts here, as I said, but this is the logic. You understand what's the width based on the prong here. So let's look at the example. I like the code. So when we look at the code, you know what we are talking about. So here, and this is the working code once again, And so you can load in your package, your module, and this is the summary of the key step. I put it here. How to set up the model, how to set a database preparation, how to the low rank training configuration, and then load the model here. For example, here, and we have a model we loaded, and we loaded the model here and set up the model. And there's a couple model we can play around. I think I remember I put some here. Let me see if I have. Okay, this is the model I play around. Use this code. We can do a DeepSeek R1. I try to trim, the small one they published. Use this one. Oh, you can use Anlos Meta 3.1. You can use 5.2, the Microsoft. Oh, you can use the Tiny Llama one, and you can couple one. You can play around, okay, and then you can with outside output director. Then is the model tokenized, the similar thing like we create or training. So you build all those, and then you do this all that kind of training. Then all that. Then we can test the model. We can come out to some result, and okay. This one I also share with you in a couple of minutes. So before we end, there's two more things we haven't really talked about is the reinforced learning. So the model already listed here. As you can see, I have 4 different wording for the reinforcement learning. You can play around and you can understand what they are talking about, why they said DeepSeek is a Distill the model from OpenAI, blah, blah. What's the PPO, the proximal policy optimization one? And this is the one working, and so you can play around. And then the next one is called RHS. It's basically the same thing, but a different version. I try to play around this one. And as you can see, this one works. And this, as you can see, the training model and how many laws. And then use next step. And you can see the result, how it looks like. And then I think this one, yeah, then you can see this one. So the earlier one, I believe I have version 1 in January 27, a couple of days ago, version 2, and total how many versions come out? Version 4. Version 4 doesn't mean the best because I try to twist around the parameter, the data, how to see, how in the end, you can play around. You found out if you have a best solution, you found a better one, let me know. So, okay, 1 hour already. So now we go back here. So all the sample code, I will copy this file and put to the chat and to everyone. So you can copy back, you can store that. And this is all the code I talk about. And so in the end, don't worry about. And I have one more important slide. Okay, here, and there's the other one called Tiny Zero. Tiny Zero. What's a Tiny Zero? So if you look at this one, and if you act on the X as a Twitter or somewhere, so something like this in here. So this I don't know, is he or she? It looks Jia Yi. It looks like a girl, but I don't know. But anyway, so then Jia Yi and he claimed it was less than $30 and reproduced the DeepSeek R10, but for cut down game. And so as you can see what he's doing and with the GitHub. And so I put this one, I try to duplicate. And what he tried to do, use a single GPU. And I also put the code, here. And so I share this one with you. And So this is the code here. And this afternoon, we haven't finished running. I had to stop because, before my talk. Looks like it's working. And you may have a small problem. But they all claim if you have two A100, we're working better. One single GPU is a challenge to duplicate that. But it is good. Many of you able to access more than one GPU. So if you can, run that one, we all can working together to figure it out. And also finally, also including how to fine-tune the DeepSeek data code. Okay. And so one thing, I'm still sharing the screen.
No.
Oh, I'm sorry. I'm sorry. Let me share the screen again. And one more thing is, this one. So did you guys see that the 2001, what he did?
Yes.
Okay, on the Twitter, on the GitHub. So take a look. Initially, I have out of memory issues. Later on, I search around. I now it looks running on the single GPU, but it's still challenge. But two 1800 is better. So this is the last message. It is your choice. So you have a basic understanding. Now you have a sample code. And what you want to do? You will go up or hang around. As I mentioned in the beginning, capacity already is sitting on top of the building on the world, or maybe top of the Himalaya. So what do we need to do? We need to take the elevator. We need to go up. So the first thing we need to do is push the button of the elevator. So I'm looking forward to see you inside the elevator. Hopefully we can go up together. And don't lay down, don't hang around, do nothing. So the world is ours and it's yours actually. Is future is bright if we're working hard, if we go up. So thank you very much.